Hello everyone, my name is Ananya Gupta and I am from section E6. Today we will explore three fundamental types of systems that help us model the world around us. These are classical deterministic systems, classical probabilistic systems, and quantum probabilistic systems. These models play a crucial role in many areas like physics, engineering, finance, and even cutting edge technologies. Let's dive in and understand how they differ and what makes each one unique. Let's start with an overview of what we will be covering today. We will focus on three key system types. The first one is classical deterministic systems, where the future is completely predictable based on initial conditions. Then comes classical probabilistic systems, where the future is not fully predictable and randomness comes into play. Then comes quantum probabilistic system, where the quantum mechanics introduces inherent randomness and the state of system is described probabilistically. These models are foundational in understanding the microscopic and macroscopic world, and each plays a different role in the way we describe physical, financial, and computational systems. Now let's begin with the classical deterministic systems. These are the systems where the future is entirely predictable based on the current state and the governing laws. There is no randomness involved, and if you know the present conditions exactly, you can predict the future with perfect accuracy. A key characteristic here is no randomness. Everything is determined by the initial conditions and the rules that govern the system. For example, if you know the position and velocity of a planet, you can calculate its future position at any point in time. Now let's look at the mathematical representation of these systems. Classical deterministic systems are often described by differential equations like this one. dx by dt is equals to function of position and time. Now let's move to the couple of examples which will help us clarify this. Let's consider the first one, which is planetary motion. The motion of planet follows Newton's laws of motion and gravitation. With initial conditions like position and velocity, we can predict their future positions precisely. Another example is of pendulum. If you know the angle and velocity of the pendulum, you can calculate exactly how it will move over time. Next, we will move on to the classical probabilistic systems. These systems are different from the deterministic ones because their future behavior is not fully predictable. Instead of knowing exactly what will happen, we can only describe the future in terms of probabilities. For example, if we know the initial conditions of a system, you cannot determine exactly what will happen next. The future evolves according to certain probability distributions. Let's look at how mathematically we can represent these systems. We can use transition probabilities, which tell us the likelihood of moving from one state over another over the time. The probability of transitioning from state xi to state xj at the next time step is given by this equation. Now let's look at some examples of classical probabilistic systems. First, consider the roll of a dice. If you roll a fair dice, six-sided die, the outcome is completely random, but we know that each number has a probability of 1 by 6. Another example we can consider is of Brownian motion, the random movement of particles in a fluid. Although we cannot predict exactly where a particle will move next, we can describe the probability distribution of its future position. Another example we can consider is of stock prices too. Now finally let's talk about the quantum probabilistic system. These systems are governed by principles of quantum mechanics, which introduces a fundamentally different approach to randomness. In quantum systems, randomness isn't just due to lack of information, it's a fundamental property of the system. At the quantum level, particles like electron don't have definite positions until we measure them. Instead, they exist in a superposition of states, and only when we measure the system do we collapse into one of these possible outcomes. Now let's look at the mathematical representation of quantum systems. The state of a quantum system is described by a wave function psi, which encodes probabilities of different outcomes. The Bond rule tells us how to calculate the probability of finding a particle at a specific position. Now, let's look at some of the examples of quantum probabilistic systems. One of the famous experiments is the double slit experiment, where particles like electrons show interference patterns indicating they behave like waves. However, when we measure them, they behave like particles and the wave function collapses and the exact location is determined. Another example is of quantum entanglement. When two particles are entangled, the states are correlated no matter how far they are, meaning measurement of one particle instantly affects the another one. Okay, so now let's take a step back and compare all these three systems side by side. As you can see, there are fundamental differences between them. The classical deterministic systems are fully predictable with no randomness. The future state is determined entirely by the initial conditions and the laws of motion. While on the other hand, classical probabilistic systems introduces randomness and uncertainty. We can only predict the probability of certain outcomes, not the exact future. While quantum probabilistic systems are different again, because randomness is an intrinsic feature of nature. The act of measurement itself introduces randomness, and particles don't have definite state until measured. Each of these models is useful in different contexts, depending on whether we are dealing with a completely predictable system, one with uncertainty due to complexity, or one where inherent quantum uncertainty governs the behavior. Now let's take a closer look at how these systems differ. Classical deterministic versus classical probabilistic. The distinction feature is that deterministic systems are predictable, while probabilistic systems involve uncertainty and randomness due to unknown factors or complexity. Classical and quantum. The main difference here is quantum system feature inherent randomness. In classical systems, randomness arises due to a lack of information, but in quantum mechanics, randomness is a part of the fabric of reality itself. Quantum systems, the principle of superposition and wave function collapses means that particles can exist in multiple states simultaneously, and measurement causes the wave function to collapse one of these states. Entanglement connects particles so that the state of one affects the state of the another, even at the great distances. Now, to conclude, we have learned that each of the system has its own characteristics and applications. Classical deterministic systems are predictable with no randomness and are great for modeling system simple systems like planetary motion. Classical probabilistic systems handle uncertainty and randomness and are useful for complex systems like stock market and gases. Quantum probabilistic systems introduce fundamental randomness and are key to understanding the microscopic world with application in quantum computing, cryptography, and more. Ultimately, this system provides us with different lenses to understand and predict the behavior of both classical and quantum world. Thank you. Thank you for all your attention, and I hope this presentation helped clarify the differences and connection between the classical deterministic systems, classical probabilistic system, and quantum probabilistic systems. These models not only explain the behavior of our world from different perspectives, but also form the foundation of any modern technologies. Once again, thank you.